Hi, my name is Hyunjeong Kim, and I'll be presenting the paper. Actually, I recently graduated with a PhD in computer science from Yonsei University in South Korea. Yay! Yeah, this was the last paper I published before I completed my PhD course. The title is 3D useful comparing the effectiveness of recent reconstruction method in VR? Yeah, let's get started. People in the past tried to preserve the 3D world in 2D. 75 years ago, Polaroid made it possible to see photographs in minutes. Now, on the contrary, there are increasing attempts to create 3D models from 2D photographs. AI is turning multiple photos into 3D scenes in a short period of time. 3D reconstruction uses 2D input images to infer 3D depths by generating three-dimensional representations of subjects using computer vision techniques. There is a growing number of 3D reconstruction methods that create virtual 3D models of real objects. As many of you know, representative examples including neural radiance field and 3D Gaussian splatting. There are also attempts to create 3D models using only single image. 3D Gaussian splatting has recently become very popular, and it delivers photorealistic 3D reconstruction with generally improved visual quality and reduced generation time compared to previous techniques. 3D draws Gaussians to create a volumetric representation in which billions of Gaussians can be used to recreate complex real-world environment. And 1, 2, 3, 4, 5 plus is an innovative method that transforms a single image into a detailed 3D textured mesh in about 1 minute. This is achieved by initially fine-tuning a 2D diffusion model for consistent multi-view image generations, followed by evaluating these images to 3D with the aid of multi-view conditioned 3D native diffusion models. It was chosen in the paper because it was the sota among the studies on creating a 3D model from only a single image when I am writing a paper. This is what motivated my research. Recently, research on 3D reconstruction is increasing and many new algorithms are emerging. Most reconstruction research has focused on improving algorithmic performance, for example, visual quality, rendering time, and so on. However, there is not much research that empirically verifies how these 3D results are utilized. So I was curious about when, where, and why these techniques should be used. Therefore, we conducted a study on what aspects these 3D reconstruction techniques should be effective when applied to application. So we designed a 3x2 experimental design to evaluate 3 different visualization techniques, 3D, image 3D, and video play, and 2 different platforms, VR and PC monitor. We adopted a method that allows anyone, even non-computer professionals, to easily create a 3D model. We use the smartphone camera to take videos of rotating objects from 3 angles, top, middle, and bottom of the object. In the 3D condition, we used the source code of the original Gaussian splatting paper. Using the background removed image, we performed SFM using core map to find image features, and we modeled 3D scenes from sparse point cloud after feature matching and bundle adjustment. We utilized the 1, 2, 3, 4, 5 plus demo to implement a single image to 3D condition. The Marching Cube algorithm converts it into a 3D mesh and texture, and it can input the texture color for a specific camera angle. The video play condition removes only the background of the input video, which can be the ground truth of our study in terms of visual quality. To make the object appear as neatly segmented as possible, we implemented the chroma key technique that composited the green color into the removed background to make the object stand alone. Overall, we investigate the effects of 3 different visualization methods, including 2 real-time reconstruction methods and video playback on 2 different platforms on user recognition memory and experience. So we have total 6 conditions. This is the result of 3 different visualization methods. As you can see in the figure, the result from 3D-GS and video play are similar to real objects, while the results from image 3D are not very good. This video shows a user wearing an HMD in a GS-VR condition and interacting with an object created with 3D-GS. Image rate conditions could also be interacted with in the same way. This video shows a user interacting with an object created with video play in a PC environment. Users thought it was so natural that they didn't even notice that it was a 2D video. The dependent variables are as follows. We conducted a survey asking 3 questions to identify objects. It called recognition memory, and also includes visual quality, task load, and usability. In our study, 30 participants participated in the experiment. In the result of recognition memory, different visualization methods have different positive effects on object recognition memory across platform, with 3D-GS being better for VR and video play being better for PC. To summarize, 3D-GS is the most effective method in VR environment, and video play is the most effective method in PC environment for verifying 3D results in terms of recognition memory. Overall, the participants' preferences were in the following order: 3D-GS, video play, and image 3D. In the 3D-GS and image 3D conditions, some participants reported that it was very easy to manipulate the object in VR by rotating them around, and the 3D-GS results were so close to the real objects that they felt like they were touching them in front of their eyes. On the other hand, the video 3D results were more difficult to manipulate, but the higher resolution of the result made it easier to identify objects. We asked 5 3D designers to give us feedback on our method to hear their opinions on the actual visualization method that they will use. The feedback from the designers also yielded some unexpected results. We had doubts about the usability of 3D image 3D because the results were not very good. However, the designers say that image 3D results can be applied in combination with generative AI because it can generate 3D models of single image rather than actual objects. In addition, they responded that the 3D-GS and video play results have good visual quality and will be helpful in actual work. Finally, let me just talk about the future plan. I'm planning to do a postdoc at ATH Game Technology Center. I'd like to continue my current research and expand it to applied research in AR or MR. Yeah, if you are interested in doing collaborative work, please contact me at my email at any time. Yeah, actually, I'm Unity certified instructor in Korea, so I'm good at Unity programming and also writing a paper. Yeah, if you have any questions or would like to collaborate, please feel free to contact me. And here's my LinkedIn QR code. Yeah, thank you for your attention.
Thank you very much for your talk. Any questions in the room, Shohei?
Hello, my name is Zhang from University of Stuttgart, and I have a quick question. So, in the video play condition, especially for VR, did the participants saw that see the results in stereo or just on a 2D flat screen in the VR scene?
Yeah, right. Actually, sorry.
Use the mic for your answer.
Oh, yeah. Actually, video play condition is that reconstruction method, and we need a condition that would be ground truth. That is why we use the video as input to create a condition that most closely resembles the real objects. So we use the term visualization in the experimental design and of the paper. The result of the condition looks like it's 3D, but it's actually 2D. Yeah, and it makes it look like the image is rotating in backward or forward direction.
Yeah, I mean I understand. I think how the video play works, but what we didn't get was like, is it in stereo or not?
The display.
The display.
Yeah, that's display.
I mean, because the VR headset has two displays. So did you project it in a stereo way or stereoscopic?
Yeah, just 2D perception, no 3D depths.
Oh, okay.
Yeah.
So, and I would like to know the definition of object recognition memory. What does it mean actually?
Here is the one of real question set, and there are 3 objects records the memory in. And first, feature matching. Feature matching is a question related to the features of the object. For example, what was the animal deficit and the object? Second, color matching is a question about the color of an object. For example, what color was the lead? And third, visual matching is a question about finding an image of the actual object that appeared. We use impeding features of stable diffusion to generate 3 images similar to the image of the real object, and then instructed the participant to find the correct answer among the 4 images.
Okay, thank you.
Thank you. We'll have time for a last question if anybody wants.
Sure. So image to 3D is using a diffusion model and not just regular photogrammetry? And is there a reason why you didn't compare against regular photogrammetry? Did you compare against regular photogrammetry? Oh, not on one single image, just like taking a bunch of images, like create a point cloud and then run marching cubes and then texture map, just like how traditional 3D reconstruction.
I think it. Actually, I use a demo model, so I didn't know very detailed algorithms in this image 3D models.
Okay. Yeah. Thank you.
Thanks. Let's thank the speaker again. Okay, so the next presentation is an online presentation. The paper title is still about Gaussian splatting. So the paper title is PaletteGaussian 3D Photorealistic Color Editing with Gaussian Splatting. The online virtual presenter, if I can say so, is Chenqu Ren, who is a master's student in the School of Data Science and Engineering in East Normal China University in Shanghai. And his research interests include scene representation and multimodal interactive editing. Sorry, I'm doing several things at the same time.
We propose the PaletteGaussian framework for interactive color editing and real-time rendering based on a palette and 3D Gaussian splatting. 3D editing plays a crucial role in computer graphics and computer vision, especially in realistic appearance editing, with applications ranging from augmented reality and film production to robotics. In the field of 3D reconstruction, traditional methods struggle to achieve high-fidelity reconstruction of complex scenes. NeRF, as a significant advancement in 3D reconstruction, effectively represents geometry and view-dependent appearance using multi-layer perceptrons, showcasing remarkable new view rendering quality. However, its implicit nature leads to difficulties in scene editing, and the method suffers from relatively slow processing speed. Recently, as an alternative to NeRF's MLP and feature grid-based representation, 3D Gaussian splatting has garnered significant attention. 3DGS stands out with its impressive novel view synthesis results while achieving real-time rendering at high resolutions. Proven to be a powerful representation method for 3D scenes, 3DGS holds the potential to shape new forms of media akin to images and videos in the future. The various features of 3DGS will provide crucial support for 3D appearance editing, making appearance editing based on 3DGS an urgent task. We design a 3D scene recoloring framework for interaction and real-time rendering, aiming to achieve scene-level and object-level recoloring. It supports 3 modes of interactive editing. Given images from different perspectives of the scene, we start by extracting a palette from all images to serve as initialization parameters for a learnable global palette. Additionally, we employ CalMap to obtain a sparse point cloud for initializing the Gaussian basic properties. Subsequently, leveraging the differentiable rendering framework of PaletteGaussian, we jointly optimize the basic properties of each Gaussian, the palette weights of each Gaussian, and the global palette. Finally, we can choose a color editing interaction method to accomplish scene-level recoloring. For example, manual recoloring, image-guided recoloring, and text-guided recoloring. At the object-level editing level, we first introduce Gaussian semantic attributes. Then, using an object segmentation model, we extract 2D object masks to isolate objects in the scene. Ultimately, by selecting an interaction method, we modify the object's palette, achieving object-level recoloring. Obtaining realistic and stylized recolorization effects using manual editing often requires tedious adjustment of the palette and is often difficult to achieve the desired results. Therefore, we introduce an image-driven approach to address this issue. To achieve realistic image-driven recoloring effects, we propose the iLearning, a palette learning-based method. Since the palette is shared across all Gaussians, constraining the palette from a single viewpoint can optimize the global palette. Specifically, we first employ a 2D image-level style transfer model cast to perform style transfer on a training view image from PaletteGaussian and a style reference image, obtaining a stylized image I_style. Using I_style as supervision, we freeze the basic attributes of Gaussians and the palette weight parameters. We then retrain to optimize the global palette parameters, ultimately achieving a realistically stylized 3D scene. Additionally, our method supports the embedding of different style transfer models for more diverse color styles. Here is a demonstration of the various recoloring effects supported by our work. The first is scene-level recoloring, where we modify the global palette of the scene to recolor the entire scene at once. The second is object-level recoloring, where the mask of a specific object is obtained through a click operation, and modifying the palette colors will apply recoloring to that object only. The third is image-driven recoloring, where by uploading a reference image, the scene is recolored to resemble the color style of the reference image. The fourth is text-driven recoloring, where we integrate an interface for the text-to-image model to facilitate richer interactions. By incorporating the text-to-image generative model, users can achieve recoloring for the scene by inputting relevant textual prompts.
Okay, do you have the author connected somewhere, or if you don't, then we just yeah, I think so. But is it connected? Do you have the list of participants or something? No, just wanted to see whether the author is connected and if we could ask him questions. Okay, but oh no, it's not one of those. Okay, so he's not connected. Forget it. Okay, sorry for this. It looks like the author is not connected, probably due to time difference. So what I propose is that we move on to the next presentation. Well, it's not that I propose, it's that we don't have that much of a choice, in fact. So the next presentation is entitled Neural Panoramic Representation for Spatially and Temporally Consistent 360-degree Video Editing. The presentation will be given by Simin, who is a PhD student in the School of Engineering and Computer Science at the Victoria University of Wellington. Her research interests include neural representation, image and video editing, mixed reality, and computer graphics. Whenever you're ready.
Hello everyone, welcome to this presentation.
The mic, because it's broadcasted online.
Hello everyone, welcome to this presentation. I'm Simin, a PhD student at Victoria University of Wellington, and our work named Neural Panoramic Representation. For short, you can call it NPR. As we know, VR allows users to interact with and observe the environment in all directions using HMDs. And whereas 3D modeling requires manual effort, 360-degree cameras could capture the dynamic real-world environment, offering a cost-effective way to acquire VR content. Such kind of video can be easily displayed in HMDs, so it could preserve the VR's immersive qualities. However, its interactivity is limited to compared with a fully 3D modeled environment. Like the user can just watch, not engage with the content. So this raises an important question. How can we make 360-degree videos more interactive? Let's imagine if we could modify the content so that we could achieve a shift from passive observation into active engagement. Planar video editing typically works for a limited FOV on a 2D plane, focusing on smooth transitions and temporal coherence. So, however, 360-degree videos, being spherical projections in a full spherical view, it significantly complexity the video editing process. It poses inherent challenges, like the geometric distortions, and it also needs to ensure the seamless continuity in all directions. Even minor disruption will break users' immersive experience. In the existing approaches, like the neural atlases, deformable sprite, they could learn a planar proxy to maintain the temporal consistency for planar video editing. But it struggle with 360 video editing because they are not considered the unique properties of 360 videos. And another kind of approach, optical flow-based approaches, it could model the frame-by-frame motions, but it suffers from the calculative errors and occlusion issues. Also, absence of the real-world 360-degree optical flow deceit, which means it's hard to get the very precise 360-degree optical flow to support such kind of editing. Particularly, optical flow-based approaches could not consider the global spatial temporal consistency. And there is also a scene representation for 360 data. It's named ARthroNeRF. It could learn the spherical relationships for the 360-degree images, but it's just designed for static scenes, struggle with dynamic contents, and it's also without the editability. So this brings us to our motivation. We need a novel representation that can learn global spatial temporal relationships in 360 video content. So our goal is to develop such a method, ensuring both spatial and temporal consistency for dynamic 360-degree environment, ensuring user-friendly and intuitive 360-degree video editing. To address this, we propose a fully implicit approach, and we aim to work directly on the original 360 video format. And our method is leverage the encoding power of MLPs to process the pixels that's distributed on a unit spherical surface. In our pipeline, we treat the given 360 video as a collection of 4D points in their 3D for the spatial positions in spherical coordinates and 1D for time. In this pipeline, we encode this 4D point into a 3D neural space to encode the global correspondence throughout the whole video. And in addition, to enable the intuitive editing, we developed a bidirectional neural model, which using the lightweight MLPs to support the bidirectional mapping between the original video space and learned 3D neural space. And our method have two key steps. At first, we learn a model that could encode the spatial temporal relationships based on assumption of a unit spherical surface. We call this forward mapping. And since the most foregrounds and background have different patterns, for example, most foregrounds have the non-rigid motions like walking, running, and background, in most cases, background just have the camera motions. So we separate the given video into distinct layers. In this example, we use 3 MLP groups, one for foreground and one for background, one for opacity value. And together, these layers can represent the content, the video content in the 3D neural space. Here we use 2 forms of representation. The first one is the reconstruction loss. It's for match the RGB value in the 3D neural space to corresponding its original 4D space. Another one is alpha loss. Is to encourage the predicted opacity values corresponds to its initial input masks. Additionally, we designed 2 regularizations to preserve the spherical geometric. Spherical neighborhood consistency is to maintain the consistency in relative positions by 8 neighboring pixels. It could encourage the mapping process, make the consistency in relative position between the original video space to the learned neural space. And another one is unit spherical regularization. Is to encourage the learned 3D neural position are distributed on a unit spherical surface. Well, this forward NPR could support the reconstruction of the given video. But if the user could just add it on this just kind of abstract neural space, it's not quite intuitive. So we introduced the backward mapping. It consists of mapping the learned 3D neural position combined with time t to its original 4D space. By incorporating these 2 bidirectional mapping, we could identify each position and its correspondence information throughout the whole video, regardless of the neural space or the original video space. Based on this, user could add the edit on any single original frame instead of on the abstract neural space. Here is an example, like if the user adds the stroke on the 6th frame of the video, and our learned model could propagates this edit consistently in other frames, also for the throughout the video. And here is a demo that illustrates how users could interact with our learned representation model, like draw this emoji on the tower. So let's move to the experimental result. This is the reconstruction video from our method compared with 4 baselines. As we see, our methods could show the minimal visible artifacts, unlike the other baselines. And we also evaluated on 9 all real-world videos in our dataset in these 4 metrics. And our method outperforms other baselines across all metrics. And in addition to reconstruction, we also give some examples about video editing. Like this, remove the car on this road, and add the stroke like the OK on this moving car. Add the image texture like the smile emoji on this walking guy. And the edit can also apply on the static reason, like add the logo on the grass. This is the visualization of the global correspondence. Like this tool, we could clear to see the car and the guy's motions that could consistently get throughout the whole video. And to further validate our effectiveness of the regularizations, we conduct an ablation study. Like when we remove the spherical neighborhood consistency, the dislocated issues appeared, particularly on the large region here, the ground. It's due to the loss of spatial positions, the relationships between each pixels. And if we remove the united spherical regularization, like this one, it means the learned neural positions escape from the unit sphere. It will cause the incorrect depth perception and inaccurate position correspondence. So that's all the result for our method. It's promising, but also have limitation. Like our method specializes in pixel-wise appearance edits for 360 videos with dynamics object. And it currently lacks the capability to model the temporal information. So in the future, we would like to integrate temporal modeling modules to enable video prediction and timeline editing. In summary, we propose the first neural representation to model dynamic scenes and the global correspondence for the 360-degree videos. It could enable immersive and interactive 360 video editing in pixel level. And we would say it's tailored for dynamic spherical appearances, surpass existing neural representations for 2D planar videos and the 360 static scenes. Our superior performance have been proven in real-world tests, achieving high-quality reconstruction and ensuring spatial and temporal consistency in editing. Thank you, that's all. If you have questions, I'm happy to answer them.
Thank you very much for your talk. Any questions in the room? I do have one question, is about the quality of experience of such editing. You mentioned that pixel-wise, you have pretty good results, and I fully understand that. But did this have some kind of impact on the quality of experience? You know that, for instance, 360 degrees video would be, to some extent, prone to cyber sickness. Just an example, but does the editing technique has an impact on such quality?
in this work, we just saw some demos for that, but we plan to do the user study.
I mean, just to get feeling, like, did the user, the people watching the demos told you it's better, worse? It doesn't have to be a user study, just a feeling.
I know, because this is just a 2D plan, so it could not show the entire feeling about the spherical video.
Okay, so you didn't display them in real 360 degrees so far?
But we do map it on a sphere in the HMD. Yeah, so if there is no consistency, it's very obvious, especially for some similes.
No.
Yeah.
Okay, thanks.
Thank you.
Yep.
I have a question about the parameterization. I think in the one of the slides shows that the first input is like a 4-dimensional data, like x, y, z plus t. What is the reason to have the z value for this?
I'm not very clear.
So for 360 videos, as far as I understand, if we have 2-dimensional data as the input for the positions, is enough, right? So why do you have the z value for the depth?
Oh, yeah, I see. Because each display distribute on a unit spherical surface. It's originally it's in the spherical coordinate with the arrange and direction, just these two dimensions. But it's actually we try to use just these two coordinates. It's quite like just focus on the 2D video. It will not address some sample issues, especially near the 2 poles. And also it's when convert these 2 dimension in spherical coordinates into Cartesian coordinate, it needs to convert to 3 dimension, because in a Cartesian coordinate, it needs x, y, z to represent a sphere surface. It's actually in the Cartesian coordinate, and when this with the higher dimension, it could encode more information for the positions, each spherical positions on the spherical surface.
So basically, your finding is like instead of having just 2-dimensional positions like angles from the center, it's better to have the 3-dimensional data to uniformly sample the sphere somehow.
Yes, we found that.
Thank you.
Thank you very much again.
Thank you.
We move on to the next and last presentation of this session. This last one is about the field of view enhancement of in arthroscopic surgeries using AR and NERF. Again, presentation will be given by Zherui Qiu, who is a PhD student at the Department of Computer Science and Engineering at Johns Hopkins University, Medical University. And she's also a pre-doctoral visiting fellow at the National Institute of Biomedical Imaging and Bioengineering at the NIH. She's involved into medical AR and integration with computer vision. Please.
Okay, thank you very much for introduction. I'm Zherui, I'm a PhD student at Johns Hopkins, and welcome to the last presentation before lunch. And I'm presenting our work, ARthroNeRF, and so I will start with what is the surgical procedure that motivates this work. So arthroscopy is actually a minimally invasive surgery that used to diagnose and treat joint problems by inserting an arthroscope on a fiber optic camera into a small incision, and the surgeon will also have the surgical tool from another port, so they can view and manipulate the the joint through the procedure. However, during this kind of procedure, we got several challenges. Now, what the surgeon can only rely on is the video feed from the arthroscope on the video. So it caused a problem about the hand-eye coordination because there is actually a mismatch between the location and orientation of the operative field on the monitor and the actual operative field like in front of surgeon's eyes. What further complicates this scenario is the limited field of view that they need additional mental load to identify where they are exactly location within the joint. So to further elaborate this scenario, here are two videos. And the left one simulates the observer view in front of surgeon's eyes, and the right is the video feed from the arthroscope. And we can see that when I move my tool forward, actually in the arthroscope feed, we can only see that it's towards the right direction. And this kind of mismatch is hard for surgeons to find the tooltip. And what complicates the seams further is the angle of the arthroscope. That's if we know that the arthroscope is at the 0 degree, surgeons can simply use the triangulation to find the tooltip. However, for the better visualization within the joint, the arthroscope typically has the 30 degree or 70 degree, and this can hard for them to that makes like the simple triangulation unreliable. And we can say in the real scenario, what the surgeons can only rely on is just like the arthroscope view. They cannot see inside the joint. So in this way, work, we just came up with an idea. How about we just generating the view directly from the like surgical tools perspective? In this way, the surgeons can only like focus on the alignment with their line of sight and enhance the information they receive. And the very important component of this idea is we use the narrow radiance field. That is a powerful concept for 3D scene representation. It takes like the sparse 2D images as input, and among the many variants of the NeRF, we choose the instant NGP, which is a very strong choice because it provides a faster rendering. But you may know that the NeRF-related work typically will use the co-map as an additional step to get the camera position. And it's actually have some problems in the medical setting because it cannot ensure both the tool and the camera position within the same coordinate system. So our idea is to integrate the optical trapping system called NDI, which is like commonly used in medical setting, and to use the infrared cameras to and markers to track the position in 3D space and provide the real-time and high precision tracking. And how this idea can be integrated to our approach. Here is the overview of the method. And so firstly, we will do the hand-eye calibration to determine the camera position relative to the optical tracking system. And after that, we can use the arthroscopic imaging and tracked camera position to train the instant NGP. Next, we will also attach the passive marker to the tool. This allows us to generate a viewpoint from the tool's perspective. And we actually provide 3 different viewpoints. So we provide a first-person view that the virtual camera is actually, it's actually positioned at the end of the tooltip. And we also provide the third-person view that is the virtual camera positioned 3 centimeters away at 45 degrees relative to the tooltip. And finally, we test on the combined view that is a picture-in-picture representation that merge these two perspectives at the same time. And by synthesizing this perspective, we try to determine which perspective is the most efficient in aiding users. Because we replace the co-map with the optical tracking system, what we first evaluate is the image like a synthesized feasibility, and we conclude that the optical tracking is a feasible approach to for sim reconstruction. And it also provides additional advantages. As you can show the column of the femoral head of the reconstruct images, we can find that it performs better in featureless environment because co-map sometimes is failed to capture enough features to reconstruct the whole sim. And additionally, there is no additional processing time to get the camera position because we can get the tracking position in real time by the optical tracking system. So in addition to evaluate the image quality, we conducted a user study with 18 participants, try to evaluate how the use of alternative views from the perspective of surgical tool could assist users in reaching target of interests. And here is our experimental setup. So we have the phantom model to simulate the surgery, and we have like a acrylic board that the users need to interact with to touch the center. And we have the camera that simulates the arthroscope. So this can capture the internal images, which is the target images for user to see. And we also have a surgical tool that the user can insert from the port to really interact with the target. And here is our sim preparation. We will first collect the arthroscope string and the corresponding camera location to reconstruct the sim. And then we will check the tool's location and randomly give users different orders of perspective generated by the incident GP. And using the surgical tool, participants insert it through the port to touch the target center based on the synthesized view showing on the screen. We assess the task performance using objective metrics, which is position error, the number of port changes, and the time completion. We also have the subjective matrix that to evaluate the single, for example, the usability and certification of our system. We have the single is question, NASA task load index, and also system usability scales. And here is the results that shows the touch position from 18 participants. And the black circle represents the horizontal target, and the red circle represents the vertical target. And here we can, I can further elaborate that the blue cross here indicate the first person view we mentioned before, and the yellow cross is the third person view, and the green cross represents the combined view. Our user study showed that the combined view had the lowest median position error and fewer port changes. The first person view was the fast, and in contrast, the third person view had the highest position error and took the longest time. We used a single is question to determine which view made the task easier. And we know that SEQ is actually rated from 1 to 7, which the lower scores indicate the easier task. And we also employed the 2-key HSD test to show that the third person view was significantly harder compared to the first person and combined view. And our NASA task load index also revealed that the third person view was more demanding. And while the first person and combined view reduced the task difficulty and workload. The system usability scales is average 70.83. That's that means a good usability compared to the average 68 score. In addition, we have the use case in augmented reality that we can extend this idea that we can attach the passive marker to the HoloLens, and then we can generate the images from the angles regarding to the user's eyes position towards the virtual screen, and the way then presents the rendered images directly in front of user's field of view, and use a red dot to indicate the tooltip position within the scene. Although we got like some great results, we still need to focus on the following aspect. So firstly is the camera mobility, that we need to address the limitation in arthroscopic surgeries, where the camera actually has a restricted movement. And we also need to incorporate the real-time dynamic changes in surgery to enhance ARthroNeRF's adaptability. Finally, we need to try to shift from like projecting the virtual screens to in situ reconstruction for a more immersive and real-time tool visualization. In conclude, our work shows the generating novel view from surgical tool is a feasible approach to mitigate the challenges faced by surgeons during arthroscopic procedure. And it also reduced the processing time and improving the accuracy in feature-sparse environments by using optical tracking system. And we explore the feasibility of AR integration by synthesizing images view from user's perspective. And thank you for your listening. Are there any questions?
Questions?
Thanks for your talk. I have a question. So because you have this pre-processing step, basically you need to scan the environment first. So I'm wondering, how do you transfer this into a real clinical application?
Yeah, currently this work is a preliminary study that we use to prove the concept that we can integrate it to the optical tracking system, and we know the limitation that in a real arthroscopic surgery that actually you cannot freely move your camera So next step is we will try to constrain this kind of mobility and to see how whether it's feasible to reconstruct the same quality of the scene.
All right, thank you.
Any other question? Well, I have one. NeRF have been used also to do some camera localization. So maybe could you combine this technique in order to get rid of the tracker that you have in the context?
This is our innovation, because in the medical setting we need to know the exactly position of the joint and in the 3D space. If we just use the co-map themes like structure from motion approach, it actually give you something like a fake position within a virtual theme. So it's hard for a real surgeon to integrate their tools inside the joint.
Thank you. If there are no further questions in the room, I'd like to thank you again for your presentation.
Thank you.
And this will be the end of this session. So, bon appétit, as we say in French.